plasma insulin, and this is minutes. Increase in plasma insulin concentration following sudden increase in blood glucose to 2 to 3 times the normal range. Note that initial rapid surge in insulin concentration and then delayed but higher and continuing increase in concentration beginning 15 to 20 minutes later. And this is the explanation of these phases. Sensing a rapid rise in plasma glucose concentration, the beta cells first secrete their stores of pre-synthesized insulin. Following this acute phase, the cells begin to secrete newly synthesized insulin in chronic phase, which lasts as long as the glucose challenge. In vitro, studies of isolated islet cells and the perfused pancreas have identified a third phase of insulin secretion commencing 1.5 to 3 hours after exposure to glucose and characterized by spontaneous decline in secretion to 15 to 25% of the amount released during peak secretion, a level maintained for more than 48 hours. Just to have an idea about the principal action of insulin, insulin functions on adipose tissue, muscle cells, liver cells, and in general increases the cell growth. And you see, you can understand the role of insulin on adipose tissue as well as muscle, liver, and in growth. I'm sure you had an idea about the role of insulin in growth and on entry of amino acids into cells. And the role you see mainly on all food elements affecting adipose tissue, muscle cells, and the liver on all food elements, carbohydrates, lipids, and proteins. You know that insulin is needed for almost all the cells in the body so as to benefit from the glucose. Then these are the tissues in which insulin facilitates glucose uptake. Almost all the cells: skeletal muscles, cardiac muscles, smooth muscles, adipose tissue, leukocytes, crystalline lens of the eye, pituitary, fibroblasts, mammary gland, aorta, and the A cells of pancreatic islet. But there are other cells that don't need insulin so as to benefit from the glucose. These are brain, except probably part of the hypothalamus, kidney tubules, intestinal mucosa, and the blood cells. These are vital organs. These vital organs, they don't need insulin so as to benefit from the glucose. This figure shows the blood glucose homeostasis. And this figure, on purpose, I'm showing you to have an idea about the range of blood glucose level. This is wide range. It is in the wide range from 70 milligram per dl to 110. This is the wide range. But usually the normal range from 90 to 100. From 90 to 100 milligram of glucose per dl. It is normally 90 to 100 milligram per dl. let us say, very little below 80, and also very little above 100. You see from this figure the distribution of glucose, and you see here that the brain does not need insulin so as to benefit from the glucose. Anyway, 30 to 40% of the glucose is transported into the fat cells, and they remain into muscle and other tissues, just 5% into the liver. And you see, with the blood glucose level below 180 milligram per day, usually we don't trace any level of the glucose. But when the glucose level becomes 180 and above, then we can trace the glucose in the urine. And then this level is called glucose renal threshold, 180. Above that, we can trace glucose in the urine. Below that, we cannot usually trace any amount of glucose in the urine. Anyway, this is the normal blood glucose homeostasis and the distribution of glucose into cells. This figure shows that disordered blood glucose homeostasis in insulin deficiency. You see, there is glucose in the urine because the blood glucose level is 300 milligram. There is hyperglycemia above 180, above the renal threshold. This is called glycosuria. You see, usually within certain limits of the blood glucose in the human being, the brain not affected. The entry of glucose into fat cells is affected, or distribution, also into muscle and other tissues. And you see the glucose coming from the liver more than going into the liver. And then this is disorder of the blood glucose homeostasis when insulin is deficient. Just, very brief idea about the diabetes mellitus. Systemic disease in which the body does not produce and or use insulin, characterized most notably by hyperglycemia, increased concentration in the glucose in plasma. In addition to abnormal glucose metabolism, disorders in the metabolism of lipids and protein intensify the seriousness of disease or of the disease. Superimposed on the disorders of carbohydrate, fat, and protein metabolism are diabetic specific microvascular lesions in the retina, renal, glomerulus, and peripheral nerve. The cause of diabetes continues to be a mystery in a way, although both genetic and environmental factors such as obesity and lack of exercise appear to play roles. There are 23.6 million children and adults in the United States, or 7.8% of the population, who have diabetes. Although an estimated 17.9 million have been diagnosed with diabetes, unfortunately, 5.7 million people, or nearly one quarter, are unaware that they have a disease. Diabetes have several clinical forms, of each of which has distinct etiological, clinical presentation and course. You remember when we talked about the obesity and diabetes. Obesity is closely linked to insulin resistance. The marked increase in the prevalence of obesity has played an important role in the prevalence of diabetes. According to data from National Health and Nutrition Examination Survey, 2/3 of the adult men and women in the United States with diagnosis of diabetes 2 had a body mass index of 27 kilograms per meter square or greater. We'll talk about the body mass index after a while. Diagnosing diabetes mellitus is not difficult to do. Symptoms usually include frequent urination, increased thirst, increased food consumption, and weight loss. Now we see the disorders in the lipid metabolism in insulin deficiency. Actually, the human being needs very little insulin so as the normal lipid metabolism to occur normally. The most important effect is that enzyme, hormone sensitive lipase in the fat cells become strongly activated in insulin deficiency. This causes hydrolysis of the stored triglycerides, releasing large quantities of fatty acids and glycerol in the circulation. Consequently, the plasma concentration of free fatty acid begins to rise within minutes. This free fatty acid then becomes the main energy substrate used by essentially all tissues of the body besides the brain. When the body depends almost entirely on fat for energy, the levels of ketone bodies, the keto acids, acetoacetic acid, and hydroxybutyric acid in the body fluids may rise from 1 milliequivalent liter to as high as 10. All of this extra acid obviously is likely to result in acidosis. Beta-hydroxybutyric acid and acetone, along with the acetoacetic acid, are called ketone bodies. Keto acid can be excreted in the urine. Very little of them in the acidic form, but instead it is excreted combined with sodium from extracellular fluid volume. Part of the sodium is replaced by hydrogen ion, and thus adding greatly to the acidosis. Then you see, this is the abnormality in the fat metabolism in insulin deficiency. How about proteins? The disorder in protein metabolism in insulin deficiency. Protein depletion and increased plasma amino acid caused by insulin lack. You see, virtually all protein storage comes to complete red line when the insulin is not available. The catabolism of proteins increases, protein synthesis stops entirely, and large quantities of amino acids are dumped into plasma. The plasma amino acid concentration rises considerably, and most of the excess of amino acids are either used directly for energy or substrate for gluconeogenesis. This degradation of the amino acid also leads to enhanced urea excretion in the urine. The resulting protein wasting is one of the most serious of all of the effects of severe diabetes mellitus, and it can lead to extreme weakness as well as to many deranged functions of the organ. Summary, now we'll see the effects of insulin deficiency. We know that disorder of carbohydrate metabolism, as well as now we know the disorder in protein metabolism and also in lipids. When there is disorder in carbohydrate metabolism, decreased glucose uptake by the cells. The result, hyperglycemia, glycosuria, because the level of glucose above 180. Osmotic diuresis, the osmotic pressure increases in the renal tubules because of the increase in the plasma glucose level. And a lot of urine is excreted, a lot of water is excreted. This lot of water drags with it electrolytes, then electrolyte depletion. And we know that disorder in protein metabolism, we said there is a lot of protein metabolism, increased plasma amino acids, nitrogen loss in the urine. You see here in increased lipolysis because of the abnormality in the lipid metabolism, increased plasma-free fatty acids, ketogenesis, ketonuria and ketonemia, production of ketone bodies, increase of ketone bodies in the urine as well as in the blood. The result, because of the excretion a lot of urine, because of acidosis as well as because of the osmotic diuresis, dehydration occurs. Acidosis, when the patient comes to this, to the dehydration as well as acidosis, coma and death occurs. Then the end of the patient, uncontrolled diabetes, when it ends to dehydration, acidosis, he will be or she will be exposed to coma and death. While we are talking about coma, now we understand that there is coma because of acidosis. The coma in diabetes can be due to acidosis and dehydration. However, plasma glucose can be elevated to such a degree that independent of plasma pH. The hyperosmolarity of plasma causes unconsciousness, hyperosmolar coma. Also, accumulation of lactate in the blood, lactic acidosis, may also complicate the diabetic ketoacidosis if the tissues become hypoxic. And lactic acidosis may itself cause coma. Brain edema occurs in about 1% of the children with ketoacidosis, and it can cause coma. Its cause is unsettled, but it is a serious complication with mortality rate of about 25%.